Yes, I'm Ismael. I'm from Chile originally, but I live and work in London, and I'll be speaking about a full-stack programming model for Ruby and event sourcing. So let's jump straight to it. So I built a really simple demo app in Sinatra to kind of showcase the different ideas I'll be describing here. And the app is basically an imaginary point of sale application for a coffee shop. So on the right, you can see an employee, creating an order and adding products to it. And on the left, you can see another view. And if you look closely, it's updating in real time to the things happening on the right. So there's a real-time component to this as well. And I'll be using this app throughout the talk to, explain the different points. So before talking about event sourcing, when we look at this kind of application, which is pretty standard, I think what I do and what most people do to try and understand what the domain is about, what the application should do, you try to understand the different components in the domain and how they relate to each other, right? So you kind of build this mental image, this mental model in the form of a graph, basically, a graph of nodes connecting to other nodes. So in this case, we have orders, customers, payments, products, and so on. And then what happens is that as the domain becomes more complex, as we need to add more features, for example, we start adding more nodes and edges to this graph. So now we have discounts associated to customers, we have complements associated to variants, prices, inventory, and so on. So as the domain becomes more complex, the graph mental model that we have in our heads becomes deeper. And this depth in the complexity of the graph is kind of unbounded. The more complex the domain, the more complex the mental model. And this is kind of where a lot of coupling comes from in software design, I think. So the other thing about this way of describing software is that it's really good at describing the structure and the relationships of the components in a software system, but it's maybe less good at describing behavior. So for example, if you look at this, you can understand the different concepts in the domain, but how do you actually order a cup of coffee with this mental model, right? What are the workflows that are exposed, like from the time where the customer walks in the shop, orders a coffee to the point where he leaves out the door with the coffee in their hand? How do you actually model that entire workflow? And if you think about it, that's exactly what the business probably cares about, because they are in the business of selling coffee. So this type of modeling, of kind of forming these graph-oriented images in your head, is less efficient at that. So what are the workflows, and what are the entry points into those workflows that you're supposed to be exposing in this application? So what happens is that you normally go to understand those workflows and those entry points, you go to the pieces of infrastructure where your model, your domain model, interacts with the user or with the outside world. So for example, this is a web controller in Rails, but it could be in any piece of code. And here we handle a web request, and we interact with the object model in some way. In this case, we grab an order, and then we add line items to it. This is another case. This is not a web controller. This is a background job. And here, again, we do something with the model. We grab an order, and this time we archive it or something like that. And so the kind of workflows and the entry points into those behaviors in this kind of approach are there, but they are kind of implicit and coupled together with the execution context. So one was tied to web request, and this one is tied to background job execution. And then we have things like, CLI tasks and rake tasks and cron jobs. Again, those are all kind of commands. They are all things that are exposing capabilities or behaviors of your software, but they're kind of tied to the different execution layers. So if you want to understand how to order a cup of coffee, you have to look into all these different places and kind of stitch up what a workflow looks like in your head, basically. So I want to talk about a complementary way of looking at these problems, looking at domain modeling, that is less about structure and relationships and graphs, and more about time, the passing of time. So if you look at the previous examples, the web controller, the background job, there's one concept that stays the same for all of them, is that you have a command, the intent to change the state of the system, to add an item to the order or to archive an order, etc., right? So in visual terms, you have the command on the left, and then the user sends a command, please add an item to my order, but then you want to validate that command. You want to run a business rule. So can I actually add an item to the order? Maybe the order is already closed or placed, so you can't actually add things to it. So that's a business rule. If those rules are valid, then you record the fact that, yes, I did indeed change the state of the system, and you record that in the form of an event, a fact, something that happened to the state of the system. And so the previous example was all about structure, kind of the static picture of the system, and this way of looking at things is all about the passage of time. There's a before and an after, command and event, or cause and effect. So it's all about behavior and less about structure, and time is the kind of the main axis on which behavior happens. And you can apply this to pretty much anything that your software can do, right? So you can start an order, command event, you can add an item, update the quantity of an item in the order, and so on. So you have all the causes on the right and on the left, and all the effects on the right. So, okay, we can describe every unit of behavior as a command and its corresponding effect, the event. But now, how do we actually get to the current state of an entity in the domain? For example, the current state of an order, right? So we basically look at those events, those facts that happened, and we use the data in those different events to reconstitute the current state of whatever the entity is. So here we had the command, and the command carried with it an order ID attribute, order 1. We pass that on to the resulting event. Then we look at those events, and we collect those events, and we apply them to a bit of states, and we get to the current version of that order. It's an order with an ID, order 1. And we keep going. We send the next command to that order, add item, it's a latte, resulting in an event. Now we apply that event to the current state that we had from before, from the order, and now we have an order called order 1 with one product in it, a latte. Right, so we can derive current state from historical events, from facts that have happened. And this is a good segue into explaining what event sourcing actually is. For anyone who's not familiar with the pattern, I'm going to describe it briefly. So event sourcing is that idea that you can arrive at the current state of any entity in a system by applying past events that already happened onto a piece of state. So you start with an empty order, and you apply those events in the order that they were produced. 1, 2, 3, 4. Order started, product added, quantity updated, and you get to the current version, the current state of that order. And if you think about this, this is not really an old idea. This is basically how your bank accounts or budgeting tools work. So you start with an initial state, 0, and then you add some money, maybe your travel budget or your salary, whatever, and then you start recording events for everything that happens to that account, debits and credits, right? So the flight tickets, hotel room, bus ticket, and then those are the events. And if you want to get at the current state of your account, your balance, you basically add all those events up in order from the beginning of history until the present time, and you arrive at the current state, your balance. So that's event sourcing, basically. On top of that, you have the concept of streams. So in event sourcing, you group events by streams, and streams are just identifiers. In this case, I'm just using strings. So, and because this is a coffee shop, my streams relate to, orders. So I have order 1, 2, 3, order 3, 2, 3, And within each stream, you have a collection of events of things that have happened to that stream. So for this particular order, it was created, then I added products, another product, updated the quantity. For the other one, I only have 3 events. And each stream is guaranteed to apply its own events sequentially in the same order that they were produced every time. But across streams, there's no guarantee of ordering, right? So it's a bit like threads. You have one thread, and the code within a thread is guaranteed to run sequentially, and then you have another thread with its own sequential execution, but in between those threads, there's no guarantee of which one is going to finish first, right? So this kind of primitive, events grouped by streams, provides a unit of concurrency, basically, just like threads. And you can model entire domains like this. So this is, again, my demo, and I'm going to show how starting, I already have events for an order. I'm going to start for the event 0, so it's an empty order, and as I apply events to that state, you see how that current state is updated. So I kind of replay the history until I get to the current state of that. So now I'm going to explain the same thing in Ruby in the simplest possible way. So I have a bunch of struct data classes representing my event types. And then like order started, item added, and some of them have attributes for the things that they care about. So the item added one has a product ID and a name and a price. And then I have the history for an order. And it's just an array of event instances in the right order. It was started, then a product was added, and so on. Then I have the initial state of an order, and this is just an object in memory. It could be a struct, it could be your own class. Here I'm just using a hash because it's so simple. So I start with a nil status and an empty hash of order items. So if I want to get at the current state of my order, I take that collection of events and I reduce over them, starting with the initial order, and for each event in the loop, I check its type, and if it's an order started, I use that to update something in the state of the order, right? I move its status to open. If the event is an item added, I grab some attributes from that event and use them to add an item to the order's items hash, and so on and so forth for all events. So when I get to the last event, I now have the current state of that order, which is a hash with an items key, and I have a latte with a quantity of 2, and so on. So that's why it's called event sourcing, because you source the current state of something based on events. And to round up the entire thing, this is the full life cycle of basically an event-sourced request, right? So in comes a command at the top, and again, a command is a user's or a client's intent to change the state of the system. It could be a web request, a form, an API request, a task. It doesn't really matter. So first thing I do is that I go to the event store, and the event store is a special database whose only job is to store events. So it's a really simple database. It's basically an append-only log. You can only append events to them, keyed by streams, and then you can read past events from it. That's all you can really do with it. So it can be a file, it can be a database, it doesn't really matter. So I go to that store, I grab past events for the order that I'm trying to update, and once I have the current state, I can run business rules, validations. So I can say, is the order open for new items? Check. Maybe there's a rule that in this coffee shop, orders can have only up to 5 items, maybe, for some reason. I can also check that, right? Looking at the current state. If all those validations are okay, I can go on and update the state of that order just by appending a new event to its history, right? And that goes back to storage. So now my order state is updated forever. So again, in the demo, just going to play this. You can see as I send commands to this order, just clicking those buttons, adding products, that sends commands and events to the backend. You can see the commands and events arriving there, and you can see how the state progresses through that history in real time. Okay, so how do you actually use event sourcing in a kind of full stack application? It turns out that you can't. Because event sourcing is only, its goal is only it's a mechanism for updating the state of a system. It's not really meant for reading and querying the system, right? Because imagine, okay, you have millions of events representing thousands of orders in your event store, and now you want to have a full text search index, or maybe a paginated list of the recent orders that you have. You would have to go and read millions of events, collect them and group them by order ID, and then paginate them. It would be really inefficient. So you just don't do it. It's not designed for that. What you do instead is that you basically use event sourcing alongside CQRS. CQRS stands for Command Query Responsibility Segregation, and it's another architectural pattern. And what it means is that you split your data model into two different data models. The first one on the left is the command model, and that's the data model that's optimized for just updating the state of the system. And this is where we use event sourcing, as I already explained. But then you have a separate data model that's optimized for the UI or for the client, right? So this is where you just have search indices and caches and lists, materialized views, whatever you need, files. And then you have in between, you have a mapping layer between the two. So as events arrive at the store from state changes, the bit on the query model on the right listens to those events and updates the different views and artifacts that you need for the UI. Again, you can be updating Elasticsearch or Redis and building analytics. It doesn't really matter. But the thing is that because of event sourcing, the query side, that these views optimized for the UI, you can throw them away because you still have the full history of everything that happened in the system. So you can create a new view. You want to, you were using Elasticsearch and you want to switch to Postgres. You throw Elasticsearch away. You write a little script that pulls events from the event history on the left, and you rebuild the entire view that you want to show to your users. So that's end-to-end event sourcing in a nutshell. Now I'm going to go back to talking about domain modeling and timelines, but as I go, I'm also going to show videos of the thing working, but also code that I'm writing to support all this. Okay, so we're here. This is kind of the basic unit of behavior in this timeline-oriented view of the world. So you start with an event. For every feature is an event, becomes a command that becomes an event, and from there you can derive current state. And I'm going to show bits of my current implementation here. It's totally work in progress. So I'm going to start with a little Ruby class representing an order, the state of an order. This is not an active record thing, it's not a database thing, it's just an in-memory struct, really, a bit of data encapsulated in a class. So the details are not really important. It's an order with properties, it has items and some helper methods to add an item to it and maybe get the total by summing up the items. And this is how you use it. You instantiate it with an order ID, and then you can add products to it and get the total and that kind of thing. Next, I'm going to define the pair of commands and events that describe an entire slice of functionality, how to add a product to an order, right? This is basically a tiny protocol of the features that you're offering to your users. So first is the command, and these are just data structs. I'm using my own library for just having attribute validations and coercions, but you can think of these as just structs. So the first one is the add item command, and it has attributes. And then the second one is the event. So the first one is add item, and the second one is item added, kind of the mirror image of it. And in this case, they both look the same. They have the same attributes, but their semantics are different, right? So the command is an intent to change the state, and it needs to be validated because it might fail. But once the command is validated, it produces the event at the bottom, And that is an immutable fact, right? So that stays in storage forever. So they have different semantics. Next, I'm going to write an order actor class. And in my implementation, an actor is a class that encapsulates everything that can happen to a stream of events. So in this case, everything that can happen to an order in this application. So I start by defining what the initial state of an order is when I initialize one of these things in memory. And here I'm using that little order state class that I showed before. Next, I define what commands does this actor support. Again, here I'm registering that add item struct and giving it a command handler, a block. So every time that I send an add item command to this actor, it will go to this block, and here is where I validate what needs to be true for that command to go ahead and produce an event. So in this case, I need to check that the order is open, and also that there can be more than 5 items in the order. And if all those things are true, then I go ahead and I produce that item added event, in this case with the same payload as the command. Next, I define the event handler. Once I committed that event to history, now I can use that event to evolve, to update the local state of that order, right? So every time that I have an item added event, I go ahead and just add an item to that order. So this is how that tiny bit of functionality works. So as I browse the catalog, click a button that sends the add item command, which results in the events. And with that event, I update the order. OK, so now I'm going to talk about workflows. I mentioned that we have this kind of tiny slice of functionality. It's always a pair of commands and events from which I can derive state. Now I'm going to stitch those things together into a workflow, right? So I had one event, command add item, that results in an item added event. From there, I can derive a list of currently open orders. And then I can have a staff member, the cashier maybe, look at those open orders, pick one, and continue to act on it. So maybe send another command to update the quantity of one of those items. And that results in a new event. And then I keep going, right? So now the cashier is ready to place the order, so they press a button on the UI that sends a command to place the order place event. From there, we can derive a new view, a new list, for the barista to come in, look at the placed orders, and start preparing those orders, right? Fulfilling those items. So I'm stitching workflows out of little behavior slices, little timelines. So here, I'm looking at that feature. Oh, yeah. So I go to the placed orders, I click on one, and I start fulfilling one of those, the items in the order. And in the meantime, you can see the list of placed orders, how it reacts in real time to the changes on the left. So as soon as the order is fulfilled, the order will disappear from the list because it's now fulfilled. It's not placed anymore. There you go. But what about that list, actually? How did I build that list? Because so far I've been saying that you can use events in a single stream to update the state of a single order, right? And that's easy. You do that in memory. But lists are a bit more complex because you are actually pulling events belonging to different orders, and you want to collect them and build this list. So that's not very efficient to do in memory. So for that, you use projections. And a projection is basically a bit of code that as events happens, they use those events to update these little pieces of data and then store them back somewhere to some storage, a database or a file, doesn't matter, so that you can build those lists that are really easy to query by the UI. So a projector, in my code, it's a type of actor as well, in that it also reacts, it starts with initial state and reacts to events. It doesn't do commands because it doesn't need to. It's kind of a passive consumer of events. So here, because that list is so simple, it only has, the status, the order ID for that link, and then just the minimum amount of product data to build those little boxes. So I'm just going to use a hash for state. That's all I need, right? So that's the initial state. It has the order ID, nil status, and an empty set of items. Then I tell it what events, what order events it cares about to update that list. And it doesn't have to be all of the events emitted by the order, only the ones that the list needs. So in this case, I care when an order becomes placed, and I just use that to update my little hash of state and change its status to placed. Then I also care when an ordered item is added to the order, and in that case, I just update that little hash of items, and I don't need the entire set of product information. I just need the fact that there's one item, and it has a fulfillment status of open. That's how it starts. And then I can keep going with those events. The third one, when the item becomes fulfilled, I also update the fulfillment status to started, and then fulfilled. And finally, when this projector class is done handling events, I have this block, sync, which basically runs arbitrary code after handling an event. And in this case, I'm just taking that little hash and just saving it to the file system as a JSON blob. That's all, right? Here, I could be, if this were more complex, I could be saving it to a database instead, or to Elasticsearch or Redis. In this case, for the demo, I'm just saving it to a file. So that's how you build those projections. So now I'm going to talk about concurrency. So far, I've been describing these workflows as things that happen sequentially. For the same order, my runtime basically guarantees that all commands and events for the same order are going to run one after the other. That's kind of a guarantee that my application is supposed to give the user. So that's why I call them actors. It's like the actor model. But sometimes you do want to run things concurrently. So in this case, let's say that the coffee shop wants to allow the preparation of the order, the barista to start preparing the order even before the customer has paid for it. Maybe it saves them a couple of seconds. Doesn't matter. The point is that it's a business decision. So because it's a business decision, it should be part of the model, right? Concurrency should be front and center in the model. It shouldn't just be a configuration or a detail of implementation, right? So the business wants those two things to run concurrently. Therefore, we represent that concurrency right in the model. So in this case, what happens is that when I'm ready to pay, I start the payment process that emits the payment started event. And then I have something in my code that will react to that payment started event and spawn off a new stream called order one payment that will run concurrently from the parent order, doing its own thing. It will have its own life cycle of commands and events. And then when and maybe it will interact with some third-party payments API, for example, that might be costly or slow. And when it's done, it will notify back to the parent order by sending a command as a confirmation back to it that, yes, the payment is now done. And because these two things are running concurrently, in the meantime, while the payment is processing, the order can keep doing its own thing, commands and events. In this case, it can start the fulfillment process. So in my code, that looks like this. I already mentioned the command handlers and event handlers, and there's a third macro, and it's called the reaction handler. So here, an actor can react to its own events. After those events have been committed to history, I can now react to them. I can actually also react to some other actors' events. So here, I'm listening to my own payment started event, and in the block, I get the current state of the order and the event itself. And I have that little stream for helper, and here what I'm doing is I'm starting a new stream. And remember, streams are just strings, just identifiers. So here I'm just building my own stream identifier for that payment, the order ID dash payment, and I'm sending a command to it. And the runtime will automatically see that and start a new thread, basically, and start processing that command concurrently. That's That's the start command that I'm sending to a payment actor. It's a separate actor. And this is the payment actor. Again, it has a little initial state, just a struct in this case, and it defines the commands and events for its own life cycle. So I start with the empty state for this payment. I handle the payment : start command, and in this case, I just go ahead and emit the event started. And in the event handler, maybe I need to update the state or do something else. And then the payment actor, again, reacts to its own started events, and here it calls to the expensive API call, the third-party payments gateway. And if that's okay, if the API responds that yes, the payment was done, I can again create a stream identifier for the parent order that sends the original event, and I can send a command confirmation back to it, confirming that the payment was done. And this is how that looks in visual form. So this is now the payment actor. So it got a payment start command from the order that resulted in the payment started. And then there's that reaction. So it reacts to its own payment started event. And this is where the side effects happen. This is where I call out to the third-party APIs, which may take seconds. And if that API responds, then a user responds to populate a new command that I can send back to the order, confirming that the payment process succeeded. So this is an important aspect to it, that side effects happen in those reactions, and those reactions are the things that are gluing those workflows together. So the commands and the events themselves are basically an accounting system for your domain, right? And they are deterministic. They only take known data in the command attributes and the event attributes, and given the same data, they always do the same thing. Any side effects are relegated to the reactions, right? So you can think of those reactions as another type of user who's looking at changes in the domain, interacting with the outside world on behalf of the domain, and then notifying back to the domain by sending commands to it. So here we can see that bit of functionality. I start the payment, and in the meantime, I start fulfilling those items. You see the item events, and later you see the payment that's come back after the fulfillment events. And then I have this view. I'm going to show this bigger in a second. This is the correlation view where I can actually audit the entire workflow, including the interaction between those two actors, the order and the payment. So that's event correlation. I'm going to explain that concept first. So my implementation, basically for every command and event that you send and handle, it will track the event causation and correlation for you. What's the causation? The causation is basically the first command caused the first event in the order stream, which then caused the first command in the payment stream, which caused the first event in the payment stream, right? So it's basically the causality chain. That's the causation. And the correlation is that all of those events in this workflow are correlated by the first command, which is the one that started the workflow in the first place. So with that data, you can build views like this that show you exactly what happened in a process, even though it's concurrent things talking to each other, right? So it started with the UI sending a start payment to the order actor, the order stream. That resulted in an event. And then that order sent a start command to the payment stream. It started a new stream. And you can see the version numbers in black and white. When the order started the payment, it was at version 24, meaning that in that order stream, there were so far 24 events and commands. Then it starts a new stream, and you can see that it's a new stream because it starts in version 1. Then the payment does its own thing. It talks to the third-party API, and when it's done, it reports back in number 29 back to the parent order that initialized that payment. But when we left the order above, we were at version 24, and when the payment reports back to the order is now at version 29. And that's because in the meantime, while the payment was running, the order kept doing its own thing and fulfilling those items. So we can actually see the concurrency here. So it's really great for audit trails and debugging things. Okay, so now I'm going to talk about automation. So one thing that I forgot to say about this view is that you can see the user here. You can see the operator of this application right there, right? So the operators, like in this case, the human employees operating the domain, are right there in the model, right? They are not like use case documents somewhere else or persona profiles. They're right there in the model, right? And basically, they sit above the domain, interacting with the domain and driving those workflows forward. So here, what I need, the new feature is that, okay, I can confirm the payment. I can also fulfill the order. But now I want to listen to those two things. And once an order is both paid and fulfilled, I want to put it in a list of orders that are ready to deliver back to the customer. And because the payment and the order run concurrently, those two events can arrive at any time, right? So I need to detect when those two things happened in any order, right? And once I have that list, the employee can look at the list and say, yeah, this order is ready to deliver. So they take, the coffee, they give it to the customer, and they press the button to deliver the order, which will feed back into the list and remove that order from that list because the order is now delivered. So to build that list, I will build a new projection that's listening to relevant events. Again, it starts with a little bit of initial state. Again, I'm using a hash because it's so simple. ID, then a couple of Boolean flags to see when the order becomes fulfilled and paid, and then just a little status that I will use to know when that order is ready to deliver. So I start handling events. So I care about the order fulfilled event, and when that happens, I just set the fulfilled Boolean to true, and then I run a little helper method with the state that I will show later. Then when the payment is confirmed, which remember, those two things can happen in any order, I set the paid Boolean to true, and again, I run the helper. And finally, when the order is delivered, I set the status to delivered, which will cause the script to remove that item from the list. And then I just have that little sync block that I showed earlier, and I just save this hash as a JSON blob to the file system again, because it's easy. But again, I could be using a database or whatever. And that's that little logic to check when the order becomes deliverable, and it's just after processing the event, I check if the order is both fulfilled and paid. And if that's true, I set the status to ready, and then my sync block will only save orders whose status is ready. So that's how I build that list. And again, we can see it working here. So as I fulfill that order, it's also paid, so it appears in the ready to deliver list. And once I click deliver, it changes to delivered. So now it disappears from that list again. But that's kind of an unnecessary manual job. Like the system knows when the order becomes paid and fulfilled, so it should also be able to automatically deliver those orders. Maybe you have one of those little alarms that buzz on your table when the order is ready. So we could implement that automation. And for that, we basically replace what was before a human user, we replace it with an automation, right? So in this way of looking at things, automations and humans and any kind of operator, they all operate at the same level. They're all above the domain, driving workflows forward. So before we had a human monitoring that list of orders ready to deliver and manually clicking buttons. Now we can automate that. We have a script that's looking at that list and auto-delivering those orders. How do I do that in my code? Well, I go back to the projection, and I said that projections don't handle commands, they only handle events, but actually they can also handle reactions. So a projector can listen to events, update some state in the file system or in a database, and then it can react to those events and do something else, and basically schedule the next command in a workflow. So here, after handling the events, it reacts to that, it checks the state, and if the status just became ready, it sends a deliver order command back to the order that produced that initial event. And also here, just for fun, I'm delaying the execution of that command. So I'm saying, send the deliver command, but 5 seconds from now. So that's also something that you can do. You can have commands that will execute somewhere in the future. And I do that here just so that the demo can show how that works. So now, same thing again, but this time I'm not going to press the deliver button. I'm going to let the automation do it for me. I fulfill the order becomes ready to deliver, and in 5 seconds, it's going to disappear from that list because the automation picked it up and automatically delivered it. Okay, how are we doing on time? So the last part is that so far, throughout the talk, you've seen how, as I do things, the UI reacts automatically to changes in the backend. And I'm going to briefly explain how that works. This is not React or Vue or anything like that. It's all server-rendered templates. It's not using Turbo or anything like that. It's just really simple Sinatra application. And this is how it works. We're back with this CQRS diagram, if you remember. So on the left, we had the event source part, accepting commands and updating events. And on the right, we have these projections that are kind of basically servicing the UI. But also, when the browser connects to one of these pages, it also sets up a long-lived server-sent events connection back to the backend. And that connection just sits there, connected to the particular page on the browser, and is listening to relevant events coming from the backend. And as those events come to that web handler, they decide what bit of HTML to render and send back down the connection to the browser. And then the browser just merges those fragments into the UI seamlessly. So for example, I have one of those buttons there, and I'm using Flex, which is a really great library for doing HTML components. But this could be ERB, it doesn't really matter. I'm using Flex here. So I have these command components that you give it one of your command structs, and it knows how to build a form for it. So this is for placing the order. So I click that, it will send an AJAX request to the backend. That request will go to this Sinatra controller, where I build the command instance from the incoming parameters. I have some validation code that I'm omitting from here. And then my library is called sourced, by the way. I just ask source to schedule that command. And it will put it in a command bus, and it will do everything asynchronously in the background. That's it. That's sending a command. And then that OpenSSE connection that's listening for events, for backend events, listens to the relevant events and updates the browser in some way. So my projectors, the ones that are updating those lists, they can also emit event structs when they are updated. And these are events that are kind of transient. They are not stored in the history because they're just for the UI, but it's the same data types. So when a projector is updated, this open connection listens to those events, and if it's looking at the right page that cares about that event, it just renders some component with data and sends that HTML down the wire back to the browser. And in the browser, I'm using data star, which is a tiny bit of JavaScript that's listening on that connection on the browser, taking those HTML fragments as they come from the backend, and it merges them into the DOM really seamlessly. So, there's no page refreshes or anything like that. That's what I got. I have some extras if you're interested later. But just to finish off, the future of this kind of experimental work that I've been doing is to fix lots of bugs first. Then, if you paid attention, basically I've been describing state machines all along, state transitions. And it turns out there's a really great specification for nested event machines, state machines. So for example, that case where I had an order and then a payment running concurrently, that's kind of two state machines talking to each other, right? So there's a specification that's great for that, and there's lots of Java TypeScript implementations, and I kind of want to bring those ideas into my Ruby APIs. There's the idea of durable execution, and that's the idea that you can start some execution of code, and if it fails in the middle because of some error, you can fix the error, restart it, and retry it, and it will just pick out from the last successful event that it saw, and then carry on, right? So you can retry these things. And that's essentially what I have. That's event sourcing, but I think I want to make those APIs a bit more explicit in my code. Then the current implementation works on Postgres, and it's very Postgres specific, but I want to refactor it a bit so it can also support SQLite. It would be great for me to be able to just play with these ideas in very, very simple apps, just saving data to the file system. That'd be awesome. And finally, because I have all of those command and event specifications with attributes, and then I have a really clear DSL of how those actors talk to each other, it's actually really easy to analyze that code and build diagrams and self-auto-generated documentation out of that. Because it's a really simple protocol. There's only so many things that can happen in this code, right? Events, commands, and reactions. That's it, right? So it's easy to map out the entire execution of really complex workflows and automatically generate documentation and diagrams out of it. That's it. That's what I got. Thank you.